question now is asking us to determine the magnitude of the projected components of the force F, which is 300 Newton acting along the OA line. In the previous video we already found the components of the projected force along the x and y axis, and we found the vector, the force vector. In this case, for the second one, we already found the force vector. This is the force vector. The force vector found to be equal, F in here, equal to negative 75 I plus 259.8 J plus 129.9 K. This was the force vector we already found in the previous video. Now, if this is the force vector, we need the unit vector OA. The unit vector OA equal to the position vector ROA divided by the magnitude of ROA. So finding the position vector ROA equal, in this case, when we look at the x-axis, we move in negative, on the negative direction, 300 millimeter, which is 0.3 meter, plus this component in here and this component in here. We can find it through sine theta. It's opposite to it, therefore it's opposite divided by the hypotenuse, and we can solve for that opposite, this component in here. Therefore this will be 0.3 plus 0.3 sine 30, and that's the I component. For the J, we moving 300 millimeter on the J component, which is 0.3 plus 0.3 on the Y axis, plus for the Z axis in here will be 0.3, which is this one, the hypotenuse of this triangle in here, cos 30. Therefore this is plus 0.3 cos 30 degrees. Okay, and this is how you define your position vector. Therefore this one here should equal to, when you find this one in here, just plug that into your calculator, then find the magnitude of that ROA. In this case will be the square root of all of this. But for this one, when you solve for it, so for this one, this will be 0.45 I, negative 0.45 I, plus 0.3 J plus 0.259 K. This is your position vector in here. Finding the magnitude of ROA, this will equal to the square root of the sum of these squares, negative 0.45 square plus 0.3 square plus 0.259 all square. When you divide, divide for the unit vector UOA, dividing both of them together, the position over the magnitude, the position negative 0.45 I plus 0.3 J plus 0.259 K divided by the magnitude, which is negative 0.45 square plus 0.3 square plus 0.259 all square. When you divide these two together, you should get something like 0.75i, 0.75i, and plus 0.5j plus 0.433k. Now we found the force vector, then the unit vector, then now we need to find the vector dot product, the vector dot product. The vector dot product in this case is the magnitude of the projected component of the force itself, F along the OA line or the component, equal to F dot O unit vector OA, which is equal to, the force is negative 75I plus 259.8 J plus 129.9 K, and this is the force. The magnitude, which is, we just found it to be 0.75I plus 0.5 J plus 0.433 K. Multiply the I components together and we will get negative 75 multiplied, this one here is a negative as well. You multiply all of these together, get the I components in here together, J components again together, the K components together. When you add them, then you should, all of that should result into this one here, like negative 75I multiplied by negative 75I plus 259.8 multiplied by 0.5 plus 129.9 multiplied by 0.433. All of that will equal 242 Newton. Therefore, this is how you find the force along the line OA. So you just follow step by step in there and you shouldn't miss anything. So starting goals with finding the force vector, then the unit vector, and to find the unit vector, of course, we have to find the position vector first, then the magnitude of that position vector, then you can find the unit vector. Once we find the unit vector, now we can get the force acting along that component, which is, we multiply that the force dot UOA by the unit vector itself.